directly since 1973. So today Dave will be talking to us about using gaseous xenon TPCs for both neutrinos, double beta decay, and for searching for dark matter waves.
Thanks, Matthew. Well, it's a pleasure to be back here. Sir, Matthew, sir, went through sometime.
Yes.
Here I see it. Yeah. A few years ago, I got interested in the neutrinoless double beta decay problem, which is a problem of particle physics as to what the neutrino is its own antiparticle. And the nuclear physics associated with it is basically a nuisance. Now, of course, the DOE then attributed and decreed that this part of physics would belong to nuclear science rather than high-energy physics. So that's one of the interesting things about working in the laboratory system, is that things seem to go just the opposite way that one would think logically. So this interest persists, but it appeared that one could also possibly look simultaneously for WIMP dark matter. And it's potentially interesting because there's a liquid xenon TPC XO200 that has produced a good result on the search for a neutrinoless double beta decay. It's found the true neutrino decay mode. I'm not going to talk an awful lot about the physics of that because I want to look to the future. And there's also, as people know here very well, a liquid xenon dark matter detector. Why not do both of these projects in a xenon detector? And I want to try to make that point clear. There's a lot of speculation in what I'm going to say, but I think that as we move to more and more expensive experiments, larger scale, these things might be critical. So I argue that high pressure xenon gas, although it has the one clumsy disadvantage that to contain the stuff you need a fairly large pressure vessel, that could introduce some problems in more background because you have more stuff, but I claim that the backgrounds may be easier to mitigate in this case. So I'll talk about the synergism. There's actually a project born of these ideas, started in Spain at the Canfranc laboratory in the Spanish Pyrenees, which has 100 kilograms of enriched xenon, and will be embarking on the neutrinoless double beta decay. The shielding isn't optimum for the WIMP search, so this is not claiming to do both. I hope to have time to talk about how you might actually get to the ton scale in this game, and why it might be more than competitive for these searches with the larger liquid. Now, the start of this story began when I discovered this plot some years ago by Bolotnikov and Ramsey, published in 1997. I didn't discover it for a few years. As Yogi Berra said, you can see a lot by looking. You know, when going into the literature, you find amazing stuff. What's plotted here is the energy resolution, full width of a gamma ray, familiar gamma ray energy from cesium-137, 662 keV, as a function of the xenon density. Now, xenon, and any noble gas, is one of the few substances where you can actually vary the density and see what happens. Something very weird is happening here. If you just look at the ionization signal only, you see that for a while, as the density increases, it's pretty constant. Bolotnikov and Ramsey had to unfold the electronic noise in their setup, which was an ionization chamber. No gain. So the electronic noise was a strong part of their signal. They deconvolved it, and that explains why some of these error bars are fairly large. Once they got up to about a little over ½ a gram per cubic centimeter in density, bad things started to happen, that the energy resolution deteriorated. Now, there's 2 points here, differing in temperature, and I don't really know what happens. Maybe Matthew can tell us, but I don't think anybody really knows. What's going on here? Anybody want to take a stab? but really, this is bizarre. Why should xenon do something like this?
I'm not allowed.
You're not allowed. Well, let's consider the implications of this. For double beta decay, gee, wow, it would be great to work down here, because you only need to look at the ionization signal, which is easy to drift over long distances without much deterioration in the CPC. So double beta decay is helped by the fact that you don't really need to look at the scintillation signal. It's clear to most people in this audience that all of the noble gases scintillate quite strongly, as well as produce ionization in response to radiation. But the scintillation is going everywhere, and it's a little hard to reconstruct it. So this is a simplification to only be able to use the ionization signal and get super good resolution. Now, the WIMP searches that use liquid xenon are working up here. And this is really bad, I claim. It's not fatal, but it's bad because the Fano factor here, which determines the fluctuations, when you put in a constant amount of energy, a fixed amount of energy, there's a constraint between how energy is partitioned between the two major paths in the noble gas, the scintillation channel and the ionization channel. If you didn't put in a fixed amount of energy, such as divided by a gamma ray, then you wouldn't have something like this. This F factor goes into the estimation of fluctuations. Here it's less than 1. For the liquid state, it's calculated or measured in some sense to be 20, according to one of the earlier liquid people. So what this means is that there are huge fluctuations between light and charge when you get to the liquid state. And this causes problems for the WIMP search because the electron and nuclear recoils are not very well separated, not nearly as well separated as you would like. So, down here though, these fluctuations are small given by this small Fano factor, and I'll get into the arithmetic about this. So the resolution ought to be a lot better. So I've said this already, that in the liquid state, very large fluctuations occur between light and charge, and they compromise the discrimination power between electron recoils, the major background in these, and nuclear recoils, which is the signal. These are widely regarded as due to the delta rays which occur in the electron recoils. And these are zones of high ionization density. They're relatively few in number, they have wide dispersion in energy, and they display Landau fluctuations. And it turns out that in these regions of high ionization density, the conduction band in liquid xenon essentially delocalizes the charge carriers, and nearly complete recombination can occur. Now, Matthew might say it differently, or I'd say it better, but this is how I understand what's going on. In the gas, the conduction band doesn't exist. So this is why these low densities, like less than 0.5, you don't have this. You can have the high ionization density, but in the gas it's spread out. There's no conduction band. So the recombination follows more normal processes. So this is thought to be the more or less simple explanation of why the gas in the liquid phase behaves so differently. There's also a different way of looking at this. People say that the scintillation signal is anti-correlated with the ionization signal. This is some early data from Excel, where they plot the signal from the scintillation on this axis and the ionization signal. And if you can take a projection through at some angle, you do better. But in practice, you cannot detect all of the scintillation light, so you cannot fully recover the resolution. In practice, the efficiency for capturing the scintillation light given geometric coverage of your detectors and the quantum efficiency of the phototube. Altogether, 5%, 10% may be possible. So the statistics of your energy resolution is dominated by the contribution from the scintillation, which you can see isn't so well measured here. how does this go? It's just another way of looking at the same effect, that there are large partition fluctuations between energy and energy going in ionization and energy going in scintillation. So here's a plot I stole from Rick Geatstill's WIMP site, and it shows as a function of the energy along this axis in both cases, gamma events up here and neutron-induced nuclear recoils down here. And what's plotted here is a familiar way of presenting data in the liquid xenon world, the logarithm of S2 over S1. S2 is the ionization observed in the event, and S1 is the scintillation energy observed in the event. Now there's a faint blue line here which shows the average of the gamma rays, and there's a band here which is the average of the nuclear. And to stay away from all this stuff and get good discrimination, at that time they had to choose a fiducial volume below this average, so that about half or more of the events were lost just by that cut. So you lose a factor of 2 from that. In this, the way things usually is done slightly different, but these fluctuations that you see here, they're not getting better with energy. Whereas a single site event due to a nuclear recoil here does show that it more or less is getting slightly better, although there's dwindling population here. So you get maybe a factor of 100 by doing this in discrimination, but you pay a price. Now this is corresponding to that phantom factor of 20. What would things look like if the phantom factor were 0.15 as in gas? So my colleagues in Valencia, Spain, did a simple Monte Carlo. It's idealized, and it looks like this. And assumed the phantom factor of 0.15, and 10% exclamation optical efficiency. That's a little optimistic, but I'll argue later that I actually think we can get this in a big system. So wow, I mean, here's a very narrow band. The absolute scale here is just related to the gain factor in your system, so there's nothing really. The important thing is where does with the nuclear recoil band fall in the plot. There isn't data on the nuclear recoils in xenon gas, so we have to make some guess about it based on the what we know and what we think we know. So I made some calculations which are, not highly defensible, but it might fall here, 2.1, about 1.7 away from the, and if that were true, and if the band has a similar kind of fluctuations, the discrimination would be incredible. In practice, the discrimination would depend on designing your detector so that if you see light and see ionization, you always get it from all parts of the detector with understandable efficiency. Because otherwise you can get events that fall in strange places because your collection efficiency of one of those signals might not be so good at a corner or an edge. So this is very stimulating. It's an idealized simulation. But I wouldn't be surprised if reality wasn't so different from this. So, again, just kind of summarize, for the WIMP search, the fluctuations really compromise the electron-nuclear discrimination. And these are intrinsic. It's not because the experiment was done badly. It's a property of the material. So the discrimination can't really be improved in the WIMP search. And as I said earlier, for the double beta decay, if you really work hard, you can capture maybe about 10% of the light. And if you had captured all of the light, you could capture all of the energy by just summing charge and light with the appropriate constants. But the precision of the sum is dominated by the statistical impoverishment of the light signal, so you can't really get the resolution in the liquid xenon for the double beta decay. And why is that important? By the way, I could easily go way too fast. You're absolutely allowed to stop me and say, why you think it's such an absurd claim. Anyway, this is a cartoon for what this physical circumstances in the double beta decay search. There's a standard model process in which both an electron and a neutrino is emitted from one of the neutrons that decays. And so we get 2 neutrinos and 2 electrons. But for the zero neutrino, which violates lepton number, and would be possible only if the neutrino is its own antiparticle and has mass, because then it has an opposite helicity state, which is needed to make this decay happen. And we know that the neutrinos do have mass, so this is more likely to occur than before we knew that. So we'd like to see an extremely good, extremely narrow peak at the end of the 2 neutrino spectrum without backgrounds anywhere else. Because if you do get backgrounds in the region of interest, your sensitivity to the neutrino mass from this experiment goes as the 4th root of running time rather than the square root of running time, because there's no background. And if your resolution isn't very good, these 2 neutrino events can start to creep into your region of interest. And that is basically a fatal transition from the square root to the 4th root of time. So you need something better than the 1% to avoid including some dangerous and nasty gamma ray lines, which are not too far away from the Q value, which is about 2.5 MeV for the xenon 136 case. So here's another little study which shows as a function of how much integrated exposure in kilogram years, the sensitivity to the effective mass in the double beta decay. And I apologize for skipping all of that theory because I really want to get into the things that we don't know. If you have no background, you can start at the end of the pack here, and eventually you win. This is a propaganda slide for the next experiment, where we do think that our backgrounds may be sufficiently low that we will catch up to the winner, which ought to be Quarry, but we have to see. There's no evidence yet that the neutrinoless double beta decay really exists. The neutrino might not be a Majorana particle. We just don't know at this point.
The difference in scaling is just that these are other ones are background limited. Is it?
Yes. So, yeah. All of these experiments, except Gerda, has we don't know what the backgrounds will be. Gerda is a germanium experiment, but they have backgrounds because they are a bunch of little hockey-sized modules, and the surface events come in, and the alpha particles put a direct range all over the place. Whereas in the TPCs, there's a single monolithic volume with a virtual fiducial surface that's fully active. So it's not inconceivable that we'll maintain the square root of dependence for quite a while. Now I want to, this is kind of the background, I want to switch to stuff that we've actually been doing and stuff that is actually real. And here is some measurements in our lab, again taken with the ionization signal only, for the same 662 keV gamma ray and a little TPC at Berkeley, which I'm going to show you about. And here we get 1% forward at maximum for this. Not bad. I might have been able to fool you into thinking that was a germanium plot. But germanium is actually a factor of 3 better than this. And why? Maybe a factor of 4 better, but it depends on the implementation. The amount of energy to make an electron-hole pair in a semiconductor is about a factor of 6 lower, or 8 lower than in the gas. So there's just better statistics for the germanium than the case of the noble gas. It takes about 25 electron volts to make an electron-hole, an electron-ion pair in the xenon gas. We're really proud of this. This is a world record, as far as I know. Nobody's close. This is xenon has acquired a really bad reputation. People had implemented various detectors for gamma ray detectors, not for double beta decay, and they all worked kind of badly. But we've shown that we can actually do this, and I'm going to show you what we did. So here's the blow up of that region, and it really is a nice pretty Gaussian peak. So the kind of TPC we're operating and actually building in Spain resembles this cartoon. There's a single monolithic volume with a virtual fiducial surface that you can define after the fact, fully active, no holes. An event here produces 2 electrons, and in the gas you can see this event there about that big in a 10 atmosphere xenon TPC, so you really can see what's going on. There's a lot of multiple scattering. The one characteristic feature is that as the electron peters out, it scatters more, and so in a 2 electron case coming from the common nucleus, you'd see 2 of these. And this is referred to in our group as spaghetti with 2 meatballs, whereas a gamma ray with a single electron would give you spaghetti with 1 meatball. So this is a powerful topological feature. In addition, gamma rays coming in can produce multiply isolated, multiply segmented events from Compton interactions. And it's very hard for a gamma ray to look like this. So the rejection factor is a factor of more than 30. And this is 30 times 4 because you also see a gamma ray from the photoelectric effect at 30 kilovolts 88% of the time. So the rejection factor due to having topological information can approach 10 to the 7th or 10 to the 8th, but I can't defend that. These simulations are done in Valencia. So the TPC here takes this track, drifts it down to this purple line, which is an electroluminescent region where the electric field suddenly got a factor of 10 higher, say. And in this region, the electrons in this track can gain energy and excite the xenon, and the xenon makes light. You may think, geez, why would these guys do that? So we make a lot of light, and then we detect it over here with a bunch of photosynthesis. So we've got separated function in a sense with this device. We do tracking here, I'll talk about that so that we can see this event. But we measure the energy by standing off and integrating this light. And there's a reason for it, and I'll get to that next. So the electroluminescence is a unique tool in the armament of high-energy physics. It's essentially noiseless. What's happening in an electroluminescent plane like this cartoon here is you put a fixed amount of energy in and they produce some electrons and they drift down, they pass through a transparent grid into a high field region where the excited xenon atoms emit light. Every time the electron reaches 8.315 electron volts, it's capable of exciting a xenon atom. And it loses its energy, and then it starts over. So this is a sequential gain process. There's no exponential increase. In an exponential gain mechanism, early fluctuations in where the gain mechanism starts are exponentially amplified. We cannot reach the energy resolution that we have using that kind of gain. Here we have a linear gain system. Well, the gain isn't all that much, maybe 1,000, that's enough. But it's almost noiseless because the electron is falling through a fixed potential. There's something equivalent to a Fano factor, an analogy here, that the fluctuations in how many UV photons are made are smaller than what you would guess from 1,000. Let's say the average gain of 1,000. The fluctuations can be even 1% of the square root of 1,000. It's noiseless. It's really fantastic. And what happens, though, is that the light is going everywhere. I'm not going to take time to read all this. I pretty much said it. We reflect these fluctuation reductions by a factor called J. CP here doesn't stand for charge imperative. It stands for Conde Policarpo, the Portuguese pioneers of the electroluminescence. It can be as small as 1.01, I'm sorry. So moving ahead, the idea is that we have this event, we drift it, we convert it to light, where we have now got enough light that we can measure with precision, and we haven't lost the intrinsic resolution. It's amazing how small some of these numbers are. We're going to get to that in a minute. Lots of other virtues in the electroluminescence, as I said, it's linear. We're not very sensitive to high voltage fluctuations and stuff like that. It's immune to microphonics. Even in a germanium detector, people have to work hard so that their wires don't jiggle even though there's no gain. It's fairly tolerant to losses. I'm not going to talk about that. There's no space charge because we're not making any. The ions go the other way. There's no aging because we're not doing any nasty stuff around wires. The isotropic propagation of the signal is actually a virtue because the signals are huge and we want them to be distributed over a large number of phototubes so that we can measure this light signal with enough precision. So we do everything with optical detectors, even though we're interested in the ionization signal. Seems odd, but nobody's done it as well as we have. So our little gizmo at Berkeley looks like this. There's a TPC. The little one is about 14 centimeters across from one diameter to the other. A bunch of phototubes here that's looking at the light that's made down here in this electroluminescent gas. These phototubes also look at the primary scintillation, which occurs very quickly after an event happens, within about 50 nanoseconds. But the drift of the ionization is very slow. It's like 1 millimeter per microsecond. A long time later, you start to see the light fade down here. We need some buffer regions to grade the potential down to 0. So we might have minus 20 kilovolts here and plus 20 kilovolts here, so we can't just leave those voltages dangling. We have to control things. So we used the pressure vessel we borrowed from our Livermore collaborators. We added this weird snout to be able to get all of the signals out without having to change any of the holes or anything that would require recertification. So I've got to keep moving here. It looks like this. These little 1-inch phototubes can take the pressure. They're in the xenon gas. And we discovered something interesting about that. Field gauges on the outside. There's Teflon on the inside, which allows one to get some reflectivity. By the way, this light is in the deep ultraviolet at 173 nanometers. So it's quite difficult to detect. You have to use quartz window phototubes. And there's what 19 of these 1-inch phototubes looks like in Hamamatsu. And there's the setup in the lab at Berkeley. Pressure vessel, snout, valve to separate pressure from the vacuum system, residual gas analyzer, storage vessel, flow meters, pump, and there's getters here. There's also a hot getter that's not so visible. And after a while, everything works and it's pretty reproducible. So, again, I inflict our wonderful plot on you. And I want to show you what some of the signals look like that give this resolution. The first thing that we have to correct for is that there is some attenuation as the electrons drift because of the residual oxygen and water and whatever there else might be, but it's mainly oxygen in the gas. So we lose a tiny amount of signal when we drift over this distance, but we certainly have to correct for it because we're interested in parts per thousand affecting the resolution. So we know how to do that. The signals look like this. Here's the primary scintillation. And then a long time later, you start to see these very jagged events. There could be Compton events, multiple Compton events followed by photoelectric. But if you integrate all of the area, you get the energy. What we discovered to our displeasure is that there's some stuff here. This is after pulsing. It comes from helium and some hydrogen that's captured in the quartz. Our theory is that the xenon basically seals that helium in it. When the tubes arrived, they were in equilibrium with the helium in the atmosphere. The xenon fills those pores and the helium has to go into the phototube. And it degrades our energy resolution in a way that we can correct for it. It's a surprise. Another event looks like that, complete separation in time because of the Compton event. We actually detected, here's the S1, and we use these X-rays that occur quite often. This is an X-ray from the photoelectric event, 34 to 30 kilovolts, depending on the shell. And then this is the primary separation. And these are quite useful calibration sources for us. This is just to give you a flavor. This is the X-ray peak now. There's two of them, whether it's L to K or M to K transition. This is a little worse than it really might be. We really ought to be getting 4% there, but still not too bad. And if you open up the fiducial volume in our chamber, you don't do quite as well. It's like 1.4%, and you get lots of Compton events and Compton backscatter, and this is the X-ray peak. And the reason is that there's a radial dependence in the chamber because of the reflectivity of the optics as solid angle. It's easy enough to more or less understand, we decided not to make any corrections, but to just make a flatness restriction on the event as seen by the phototubes, so that we wouldn't have to make any radial correction. So the only correction in the 1% was due to the attenuation. We don't really know how to use the phototubes to reconstruct. As you can see, if you try doing energy weighting, you get lots of stuff that isn't quite right. We put a scintillator in to track muons. And this is a muon track, of course, it's continuous. That's why. And just looking at the flatness of the event, we were able to crudely reconstruct it, but clearly that's not good enough. Okay, let's talk about the intrinsic resolution. The fluctuations are given by this simple formula. Use the Fano factor again, and the number of carriers, like electrons, is given by the energy of the event divided by the average energy to make an electron-ion pair. For the infinite field, this is 22, but it's really more like this in our case in our density. So you calculate what the intrinsic resolution should be from this, and it should be about 6%, 0.6%. This is what Volatnikov and Ramsey derived from their experiment, even though they couldn't measure it directly. The total number of electrons in these events is like that, but the fluctuation is incredibly small. This is really getting to the point where electronics in the ionization couldn't really manage this in any size picture. However, with electroluminescence, we can convert these 1,000 times more of them without degrading the fluctuations, and that allows us to retain the intrinsic quality of the information. More stuff on this. Suppose we consider what happens at the Q value of the xenon 136. We do the same arithmetic. There are about 100,000 primary electrons. Again, the electron fluctuations are minuscule. And this is the intrinsic resolution. We can't hope to get there. If you took our result at 662, it would extrapolate to that, but there could be more systematic effects on the way, so that's an idealistic claim. Anyway, so we know what the Fano factor does to the resolution, and if we allow G to represent all of these other contributions to the energy resolution, they can be added in quadrature because the fluctuations in the deposition are certainly uncorrelated with the detection process. So F and G added in quadrature allow me to get some estimate, reasonably good estimate. And so this predicts that, I need to take a moment for this. The G factor from the electroluminescence depends on what the fluctuations were in the number of ultraviolet photons that you made. Remember, this factor could be much less than 1, and this could be 1,000, so this is negligible. The bottleneck is the number of photoelectrons that your phototube actually detected, and because they don't measure photoelectrons with perfect resolution, you have to admit a term which represents the degradation. You're really in the regime of trying to count these primary electrons. So we do the arithmetic, and we found that the sigma term is not 0.5, which I would have guessed. The after pulsing boosts this up to about 2, so this G is now 3, divided by the number of photoelectrons. So instead of needing about 10 photoelectrons, we need 20 or 30 in order to have comparable contributions to the energy. So we would expect something pretty close to what we see. We see 1%, not 1.9. There's this companion detector at Valencia. I'm not going to spend much time on this. Slightly bigger, longer drift, and they use chlorine-22 to, instead of cesium, different kind of field just to get experience. Meshes were made by James White at Texas A&M, one of our collaborators. This is what happens if you coat the Teflon tubes with TPP. That produces an improvement in light by about a factor of 3, which is a good thing to do. So this is excited with the UV. There's James White, a Spanish graduate student working on the meshes, and J.J. Gomez Cadenas, the spokesman, who's been told to keep his hands out of that particular activity. They don't do as well as we do, but we sort of understand what's going on between the two experiments because they don't have as good light collection as we do because of the longer light tube. But one thing that they're doing and we're doing is to replace a tracking phototube by a plane using the silicon PMs. These are 1 square millimeter devices from Hamamatsu. It makes so much light that if we put one of these planes just behind the EL gap, we can reconstruct the track. And the tracking that we're looking for again is to see this continuous track with more ionization at each end. And that produced about a factor of 30 improvement in the pioneering Gotthard TPC experiment in the 80s, which had only 5 kilograms. And had other problems that I don't need to talk about, but it was a pioneering experiment that showed that this topology really works. So I'm going pretty fast because that's a lot of material. Please feel.
And these meatballs, the reconstruction efficiency is really high, and how it gets
No, it's not as high as we would like because the electrons scatter and cross over, and we lose some events just because of the topological complexity. In the longer term, we'll probably do better, so I'll get to it. For now, we're probably going to have an efficiency factor a little better than half for tracking. So our tracking plane, I said this already, we have put in a new tracking plane, and so has Valencia. This is XY grid with these Hamamatsu devices, and we have some simple electronics. And most of you know what these SIPMs are. They're Geiger devices, and depending on how many photons hit at once, you get these kind of delta function pulses in the energy spectrum. So they're really wonderful devices. They have a gain of almost 1 million. And I'm not going to take any time to talk about them. We actually buy the unmounted ones from Hamamatsu for about 11 euros each. So our new, sorry for the complexity, here's the phototubes again in our device. We're going to put the tracking plane here. And it works. I don't think I included an event, but we actually can do tracking muons and also X-ray emissions. I want to turn in a few minutes remaining, and not so many, to the next experiment in Spain, developed by a joint project based on ideas originated at Berkeley. Ken Frank Underground Laboratory has been rehabilitated by Spain. They have invested 6 million euros, and we're going to need about 1 million or so, maybe 2 more, I'm not quite sure yet, to finish. This is sort of who we are, the usual Mediterranean politics. Some people come, some people go. But, we have the pioneering groups in Portugal, and it's probably going to grow. Fermilab and Argonne are quite interested in joining, and I think that will strengthen the effort a lot. That's not certain yet. So Spain did this. We're providing a lot of engineering from LBL, a lot of history. We know a lot about this, that, and the other. And here we are. We've got a big group. We had some involvement by Jim Seegers, but he decamped to the DOE headquarters. We only talk to him occasionally by phone now. A few universities, more would be welcome, and we think that we're going to have quite a lot of fun if we can get that last million to finish things. So the next detector is intended to look like this. There's a stainless steel pressure vessel. So stainless steel is actually pretty good as far as radioactivity. We thought about titanium, but there wasn't any compelling evidence that it's better. Nevertheless, we would put a copper liner around to help seal the tremendous flux of gamma rays from the laboratory walls. Stuff goes in and out through these tubes at the end. This is the so-called energy plane with 63-inch low radioactivity Hamamatsu phototubes. And they're looking at the light produced in this fiducial volume from the primary simulation, as well as the electroluminescent plane. And it's good to back off because each phototube is measuring a huge number of photoelectrons. If you tried to measure the energy down here, the phototube would saturate. You have different dynamic range requirements. You want to do the tracking here, and the energy is great. So that was kind of a conceptual advance, I think. And Teflon field cages and so on. So, you know, it's about 1 meter and 30 centimeters across and 1.4 meters in the active volume for 100 kilograms. Now, 100 kilograms is no longer of great interest, of the greatest interest, because EXO has produced a good result with 200 kilograms. We think they're going to run into a brick wall because they don't have the energy resistance. It's about a factor of 6 worse than ours will be. And they'll get into this forthwith of time. That's another story. This is a shot of the hall quite some time ago in the Chemtrack laboratory. Now there's a platform here that's waiting for us to put a detector in. So we have good support from the laboratory. We are the premier experiment of this small laboratory. Now, what about scaling up, say, to the ton? You would like to keep the number of phototubes minimized if they're looking directly at the sensitive region, because they're radioactive. They are one of the primary contributors, no matter how well Hamamatsu has improved them. We would like to keep their impact as small as possible. On the other hand, you want to maximize the optical detection efficiency. So these two requirements are obviously fighting. And when you increase the size, how do you do this? And the liquid systems typically require the PMT staring right into the active volume. I think the poster children for this are some studies done by Arasaka and all. You've got thousands of these, hundreds of thousands of these phototubes, and they are radioactive, and they're staring at the active volume. And so you have to throw away a huge amount. I mean, the number of phototubes is growing like the square of the radius, and the mass is growing like the cube of the radius. And the background should be going down like 1 over the mass, if not more, and it scales really badly, in my view. So I think this is just not a sensible way to go. Okay, now what about us? In the gas, you can use something that the liquid people have much harder, much greater difficulty. We can cover the interior of our TPC completely with wavelength shifting plastic. Because the gas plastic interface is so different, about 60% of the light can be internally captured inside the plastic, if it's born inside the plastic. However, the light must enter the plastic at whatever the optimal wavelength is. We're still learning about this, but we think there's some providential coincidences. There's a gaseous molecular additive that may do this perfectly. I want to talk about that. So if you do that, you can get all the light to a very small number of PFDs. You don't really need more than 60, no matter how big your detector is, because the energies are still the same. And we can shield these by copper. I'm running out of time, but I can at least allude to this. the wavelength shifters that I think will work are TMA, trimethylamine or triethylamine. There's some others, dimethylamine, tripropylamine. But these two are known to fluoresce very efficiently in this 285 to 310 nanometer band. And that turns out to be amazingly useful. So what we would do is we convert the image of xenon ions to TMA because the ionization potential is less. I'm going to speak at impossible speed so to get through this. This has an ionization potential of 12 volts. This is an ionization less than the first excitation of xenon. So the Penning effect will convert all of this excited xenon to TMA, and charge exchange will convert all of the ionized xenon to TMA plus. We convert the entire image into the TMA. The S1 signal will now be entirely due to recombination. That will be now at the 300 nanometers. There won't be any 173. And the S1 signal may display a columnar recombination effect. I'm talking about the nuclear recoil, which is 100 times more dense than the electron recoil. What is columnar recombination? If I have a straight track, for example, and I have an electric field which is parallel to that, all of the electrons have to run more or less past at least some of the positive ions, so the recombination is can be under circumstances much greater than it would be if the electric field and the track are perpendicular. So now I have a scenario where I might be able to detect whether the nuclear recoil is parallel to the electric field without ever imaging the track. I can do this at densities which are maybe 100 to several hundred times higher than these low pressure TPCs. So this is an interesting new idea. But I think we would do the wavelength shifting for the double beta decay as well. So we think that this will be substantial for the nuclear recoils, but maybe we should go for the electron recoil. Depends on the density. We don't know what the optimum density is. So I'm going to have to kind of skip this. We would look for a sidereal modulation in this ratio S2 for the WIMP signals. Now nobody has seen WIMPs, maybe we will. If we do see WIMPs, then we would instantly want to know, well, are they really coming from some direction in the galaxy where we think if they are not co-rotating with the galaxy, we know where they should appear to be coming from. That would be a very strong support of the WIMP interpretation. So this sidereal modulation would be every day, and it does not need a low density. It should work at high density. So we would get maybe a factor of 1,000 improvement. Just to make this a little clearer, here's a cartoon. If the winds are coming from this direction, and the TPC has got vertical here at 45 degrees, this is the Earth. 12 hours later, it's pointed in the wrong way, so that the field of the TPC and the preferential nuclear recoils would be anti-aligned perpendicular. So we can use SRIM to get some idea. Here's 30 kilovolt xenon ions going into xenon. There's a lot of scattering, but there is a preferential direction retained. This has not been quantitatively worked out, but maybe after 3 or so more preferential in the incident direction. And of course, they don't all get knocked on head-on. This is another way of looking at the SRIM results. This green line is the transverse, and this is the longitudinal. So yes, there is directionality retained in the xenon recoils. So we built a device called the T-plot, which will study these things as a function of every parameter that we can, the density, the electric field, and the fraction of molecular additive. We'll have to do this for both nuclear recoils and electron recoils, and try to confirm this plot that idealized plot that I showed you. We put in a G2 proposal for this, and we may be awarded the Chutzpah flag of merit. We don't have any data yet. This is just an idea, but maybe we'll be seen as offering such great advances that we'll get some support. It is just an ionization chamber, but also viewed by 4 phototubes from the side, so we measure both charge flowing across this and light as seen by these phototubes. And it's set up for both pure xenon, which is, it's operating now with pure xenon. Looks like this in the lab, 4 phototubes, gas system with getter, pump, flow meter, and we know enough now, we can just make this stuff work. Now in the moments remaining, I'd like to show you a little bit more about the TMA and TA. This is the vapor phase excitation spectrum of TMA when they are excited by photons of various wavelengths. They absorb these and re-radiate them. It's perfect because if you compare what the sensitivity of, for example, commercial Elgin simulators, the excitation spectrum extends from about 280 up to 310. This is we don't really understand what's going on here, probably just for having this is not a fact. But this other sample, again, has prominent inversion in the 280 to 340 region. So we think this is an excellent match that allows us to scale up to very large devices without having huge numbers of phototubes. So small chamber has been more or less designed, which has a wavelength shifter everywhere, a few phototubes. This would not be intended to actually do science, but to demonstrate the overall optical performance. And about 20 phototubes, about a foot long and a foot in diameter. And with this we could study neutron scattering on xenon at various densities and various amounts of TEA once we've established what the optimum are. So we'll see if we get any support to build and operate this thing as part of our G2 proposal. So, the ton scale, if the sensitivity to directionality, we will be able to see this as a daily thing. It's actually going to be a little bigger than this if we run at 10 bars. If we run at 15 bars, it would be this length. And it would look something like this in a water tank, symmetric TPC now with this wavelength shifting. It's not only along the sides, but it's also on the ends. The light that's born on the ends, some of it will go through and be not captured inside, and that will be enough for tracking. So here's another view that shows phototubes plus a copper ring to provide some extra shielding. So quite a beast though, rather large. And again, the phototube, we could use the same kind of pressure cans that we use now for the EL plane is shown here idealistically separated by these thin rings. And so it looks nevertheless like a possible scenario. So I've gone pretty fast. The points are that the gas phase offers incredibly good energy resolution that's important not only for the neutrinoless double beta decay scenario, but for WIMPs. The EL gain stage is a key element to reach this near intrinsic energy resolution. Now the xenon WIMP detectors do use EL, but not to gain energy resolution. But in the gas, we can have superb discrimination. I can't give you a number, but if it resembles at all what that simulation, it would be incredibly good, probably 10 to the 7th projection. So the directionality signal based on this columnar recombination idea is new, highly speculative, but still plausible. All the numbers seem to be more or less okay. That's very exciting, and I think it provides something that's really been missing in the WIMP game, because if you really want to show you have WIMPs, you have to show, I think, that they're coming from somewhere. So, to summarize, this is still emerging. We're behind the liquid people and others, and it offers, I think, some truly game-changing elements. And I do think that it shows that the era of new ideas is not over. There's no compromise that we see in the WIMP and double beta searches. They really can coexist. There's no dynamic range about it. The double beta decay events typically extend over so many microseconds that it doesn't saturate the phototube. We have a bureaucratic obstacle that the DOE has divided double beta decay into nuclear science. whereas WIMPs belong to high energy physics, so we plan to confront DOE and see what happens. Make it their problem. But
You're
make it our
interdisciplinary.
problem, too. We'll see. Now, if all this works, the directionality signal would be automatic. I mean, it's amazing. It would be a factor of 1,000 better than what the little 1 cubic meter low pressure TPCs can do. So we think that we can build a design based on the R&D plans that are partly underway now within a couple of years, and maybe get on the real axis within about 5. So I appreciate your patience and your attention. Thank you very much.
Questions for Dan?
So if the directionality doesn't work out, what kind of gains would you expect over traditional vector designs to the search?
About the same as the multi-ton, but we would have much better discrimination. So our backgrounds, I believe, would be much better as far as the electron would go. We could make much better use of our fiducial law. Neutrons are still a problem, and so I can't give you a good answer. But remember, the dark matter, if it is WIMPs, it's 5 times as much stuff as the astronomers can see. We do need a number of independent, different techniques to really convince ourselves we know what we've seen. So I don't want to say that the liquid people aren't going to succeed in seeing something real, but I don't think that it will be as convincing as the community and we would like before we could conclude, yes, it's WIMPs. It requires some very robust evidence.
Did you consider titanium instead of stainless steel?
Yeah, we did. It didn't look any better. It looked a lot more expensive. The stainless steel varies quite a bit, and you can find batches that are pretty good radioactivity.
Well, Lux studied the various grades you could get of titanium, and we found a grade that was better.
Right. To make a titanium vessel is more expensive and more difficult. And the other thing I didn't mention is that the Spanish groups have money to build a vessel, but the Spanish industry isn't really up to titanium. They would send it off to Germany, and then it's not really what they want to do. So we're kind of stuck with stainless steel from the political funding perspective. But it's not really something we regret.
I guess I had 2 questions. Following up on that one, are you worried about cosmogenic activation if it's being made on the surface with stainless?
Yeah.
A lot of stuff is stainless.
Yeah, I mean, it depends on what the cosmogenic. I'm not so worried about gamma rays because of our ability to reject them. I'm not an expert in the cosmogenic problem, so I can't give you an informed answer. We're really just working on these more basic aspects of energy resolution.
I guess my second question is, for a 100 kilogram or a ton scale detector, physically, how big is this thing?
The 100 kilogram one is about 1.3 meters by 1.4. The ton scale, depending on the pressure, could be 2 meters by about 4.5. But if it's 10 bars, it gets to be over 2 meters, and it gets to be like 5.5 meters, something like that. Pretty big. It would not easily fit down into surf, for example, which has narrow shafts.
As we found out.
Any more questions? So I have a question. I actually have a dozen, but I'll restrict myself to one here because you can just talk after dinner. So you said that the discrimination cannot be improved for liquid xenon, but do you know how there's several pieces of strong evidence, including Columbia paper from 1994, using 570 kV bismuth, and showing with half maximum ionization, and it appears that the Fano factor does go to the normal value as field goes to infinity. And at about 10 or 20 kilovolts per centimeter, liquid is as good resolution. But of course, I know the crux is getting that technologically on a large scale.
That's unrealizable.
Yeah, but you don't have to go to that crazy fields. You're already at a few hundred volts per centimeter. You're doing
No, I
not
think
bad,
you have to go well above kilovolts per centimeter. We can look at that curve.
Yeah.
It has a fairly rapid start and then a very long asymptotic.
That's true, but as you know, Zeppelin achieved 3 or 4 kilovolts per centimeter and shot at 99 point, a couple extra nines of discrimination versus xenon as a result of this effect.
Yeah, I don't think that's likely to be possible with the detector. Yeah,
Yeah.
I mean, I agree, if you had infinite field, you wouldn't get the recombination.
Yeah,
But the liquid xenon detectors have had a hard time reaching their full high voltage because of problems.
that's true, there's cathode electroluminescence and other effect. Alright, so let's thank Dave again.